So for me, it's a pleasure to introduce the last speaker of this day and this school. So Aaron Brown, he is going to give the last lecture of a stationary measure for discrete random dynamical system.
Okay, so this is my last lecture, and I'm going to end with sort of a technical lecture trying to give a proof of something. So maybe that's not the right way to end a school, but this is our understanding of the argument from Tsuji, which Marcelo just gave a beautiful lecture about Palis's work, and Tsuji was definitely inspired by this conjecture about physical measures, and this is the machinery Tsuji uses in his paper on partially hyperbolic endomorphisms to build physical measures. So maybe in that sense it's a nice argument to see, and I'll try to explain it in the simplest case that I can come up with. But the main idea is that if you have large enough dimension and you have some quantitative amount of transversality, this should give you some absolute continuity. And this is a principle that is in many, many places, and so here's it appearing again. Okay, so what is my example? I'm going to start with two linear maps on the torus, and I'm going to be completely explicit. A1 is 2, 1, 1, 1. A2 is 3, and now I forgot where I put the 2. I think I put the 2 here. 3, 2, 1, 1. Either this or it's transpose. These are positive matrices, so they preserve the positive quadrant, but actually they have a smaller cone field that they preserve. So these things are jointly cone hyperbolic. So if you go to R2 and you look at this cone, this is y equals x. You look at the cone between the x-axis and y equals x. I'm going to call that cone fancy C sub u. This cone is preserved by both of these maps. So ai of the cone maps inside of itself, and the superscript u is for unstable. So if I take a vector inside of the cone and I apply either the map to it and look at the norm, it's much bigger than what I started with, so it's bigger than some lambda u, which is independent of which map I pick. So you can check this by linear algebra. So there exists some lambda u, bigger than 1. So there's a common unstable cone, and there's also a common stable cone. So I'll call that CS. We won't really use the stable cone much, but I'll just write down. So if I take AI, if I take a matrix and take its inverse, it's going to map the stable cone inside of itself. And if I take a vector inside of the stable cone and I apply the matrix to it, the matrix inverse to it, it's going to expand that vector. So this is at least maybe strictly greater. I think I want these strict. Doesn't really matter, but strict lambda s inverse, and that's because I want lambda s less than 1, the norm. So there exists a lambda u bigger than 1, and there exists a lambda s strictly smaller than 1, so that you expand vectors in the unstable cone and you contract vectors in the stable cone. And we also have cone contraction, which I won't formulate, I'll just draw the picture. So here's my unstable cone, and actually I'll draw a distinct piece of it. So here's my unstable cone, and I can draw the image under both maps. And let's see, the image under 2, 1, 1, 1 I think is less steep. And it's hard to draw thin cones, but I'll try my best. And actually it's a lot longer. Okay, so that was supposed to be a cone. So this is A1 of the cone. And actually, A2 is disjoint from it. So Here's A2 of the cone. And the diameters or the angles get a lot smaller. That's due to the hyperbolicity. And you can just check this from linear algebra. So these cones map inside of themselves under the unstable cone maps inside of itself under both maps. You see expansion under either map, and you see that the cone gets smaller. And I didn't draw the stable cone, but the stable cone intersected with the unstable cone is just the zero set. They better be transverse. Okay, and then this picture persists under perturbations. So maybe stability of cone hyperbolicity. So my manifold for today is going to be the 2 torus, which has a, what is this called? A flat connection on it. So I can identify the tangent space with R2 in a canonical way. So I can extend my one cone in R2 to a cone field on T2. And how do I do that? I have a flat torus. I stand at the point X, and this has a canonical linear, Euclidean structure nearby. And so what do? I just take this at this point. This is my unstable cone at the point X, and I just translate it around, and translating around is completely well-defined. And now I'm going to take Ui for I equals 1 or 2. These are going to be Ui, let's see, Ui are going to live in C2 diffeomorphisms. C2 just so that we can use some smooth ergodic theory. But what are they going to be? So I equals 1 or 2. These are going to be sufficiently small C1 neighborhoods, respectively, of my AIs. And again, my AIs are matrices, but they're also diffeomorphisms of the torus. So perturb them as C2 maps, but in the C1 topology. And sufficiently small, we'll put a bunch of criterion on there later. But the first criterion we want is that if we see one perturb, this picture persists. So for Fi in Ui, the derivative at x of Fi of the unstable cone is inside of the unstable cone at the image point. I think it should, well, maybe I'll call it Fi of x. If we go in the inverse of the stable cone, and sorry, this is the stable cone at x. Sorry, unstable cone at x, stable cone at x. This is going to map inside of the stable cone at the corresponding image point, Fi inverse of x. And it's still going to expand and contract vectors. So for all v in the unstable cone at x, derivative at x of Fi applied to v is bigger than lambda u, and it can be the same lambda u, or you could divide it by 2 if you want, of v. And if you're in the stable cone, then dx Fi inverse of v is at least lambda s inverse of v. So this is just that hyperbolicity is C1 open, and cone hyperbolicity is C1 open. But this is true for any f. I perturb my f away from my A1, I perturb a different f away from the A2, I still have this uniform bound. And so, okay, this is strange board work today, but that's okay. So for n, let's see. Let's let sigma sub n be words in the indices 1, 2, Cartesian producted n times. And so given an index or a multi-index I0, I don't know why, sometimes I start counting at 0, sometimes I start counting at 1, up through in minus 1. So this is a list of n indices in sigma n. F sub omega, I'm tempted to put an n up here, but I'm going to have to write this over and over again. So I'm just going to write f sub omega is you take the corresponding map for the first index, you take the corresponding map for the second index, and you take the corresponding map for the last index, and you compose them. So f omega is just compose all n of the maps according to this index. And now for omega, for any omega in sigma n, and any vector in the unstable cone at x, if I take a word of length n and I take the corresponding map associated to it, I take the derivative, I apply it to the vector, this vector is going to grow like lambda unstable to the nth power of v. So I really have uniform hyperbolicity over all possible compositions of words of length n. And that makes this example a lot easier than when you have some sort of cancellations, when maybe the unstable of one of your matrices points near the stable of the other matrix. So this is some sort of uniform hyperbolicity of a random dynamics, that you have uniform expansion and contraction in these cones no matter what word of length n you pick. Okay, so we started with an example of linear maps. We're going to perturb them. We're going to see the hyperbolicity persists. We're going to see another nice property persists, which is the regularity of the Furstenberg measure. So if you don't get anything else out of my talk, like the Furstenberg measure is really important when you want to study the Lyapunov exponents for linear random walks or for products of matrices, and the properties of it is how you study these things. One nice property of it, so we have gamma is A1, A2. These guys are hyperbolic. They have eigenvalues off the unit circle, and they don't commute. And so this is Zariski dense, or it's a big group. It acts on the projective space. Let's see, RP1. If I take mu to be the equally weighted delta mass at A1 plus delta mass at A2, all of our driving measures will be equally weighted today. Then the Furstenberg measure, which I called nu f, I think yesterday, is C alpha holder for some C and some alpha. What does that mean? That means that if I take the Furstenberg measure of a ball of radius r at some one-dimensional plane or some vector representing that, that's less than C r to the alpha. So we have non-concentration of the Furstenberg measure. And we need something similar to this, but now once we perturb. And it's not really called the Furstenberg measure anymore, but it's the analog of this. And I hinted at the proof of this is you actually prove it with a finite approximation. And that finite approximation is what we need, so I'll state that as the first lemma. But actually, before I state the lemma, I need a picture. So now I'm going to look at I'm not sure if I can fit the picture here, but fix n and x in the 2 torus. And then let's look at all 2 to the n preimages of x. So maybe I can fit the picture here. So here's the point x, and then over here are a bunch of preimages. I'm only going to draw a handful of them, not all 2 to the n of them. At each of my preimages, I have a cone, because I have a cone field on the whole space, and the cones are all parallel. They're the exact same cone, parallel translated. And then I'm going to apply, this is one of the preimages, I'm going to apply f omega 1 to it. So for omega I in a word of length n, this cone I'm going to apply f omega 2 to. This is a different word of length n. This point over here, This is based at f omega 1 inverse of x, because this base point is going to map to x. And I want to know what all these cones look like after I map them forward under the derivative. So really, I'm going to take the derivative of these maps. These cones are going to land on top of x. And what direction do they point in? I'm pushing them forwards under the dynamics, under a very high power of the dynamics, so you expect them to contract. And so I'm going to draw them as lines, even though they have some thickness. So here's my unstable cone at x. And the image of an unstable cone is going to look something like this. This is df omega 1 of the unstable cone field. And here I'm acting on the whole cone field. I'm going to evaluate the image cone field at x. And here's maybe df omega 2 of the entire cone field. This is a new cone field on the whole space, evaluated at x. And what I want is that these two cone fields are, these image cone fields, so how many are there? There's going to be 2 to the n different cones in this sector here. I want them to not concentrate too much. And just using the proof that the Furstenberg measure isn't too concentrated, you can show this for finite time approximations. So I'll formulate that. So lemma 0. Again, taking our perturbation sufficiently C1 small. But I need one more piece of notation. So I'm going to fix a parameter, 0 less than theta less than 1, for 2 words of length n. Whoops, 2 words of length n. I'm going to say that omega 1 is parallel to omega 2, but sort of approximately parallel, if the angle between the corresponding cone field, so I do df omega 1 of the unstable cone field, df omega 2 of the unstable cone field, if this is less than theta to the n. So when are 2 words almost pointing in the same direction? It's when the corresponding image cone fields are very, very close. They're actually exponentially close. I didn't put a base point here, so take the soup over all the base points. Otherwise, omega 1 is transverse to omega 2. Being transverse is good. Being tangential is bad. So we want tangential to be exponentially unlikely. So lemma 0 says that there exists theta less than 1. There exists some alpha bigger than 0, such that for all n sufficiently large, for all omega 2s that are of length n, you count the number of omega 1s such that omega 1 is pointing almost in the same direction as omega 2. And we want to know what proportion of this is bad. So we divide by the total number. So you divide by 2 to the n. That's the total number of omega 1s. What proportion of omega 1s are bad? And this is exponentially small. It's less than theta to the n alpha. So being bad is being exponentially close. Being exponentially close is exponentially unlikely. This is some non-concentration of the analog of the Furstenberg measure under perturbation.
Sorry, in the inner case you have unique ergodicity. Yeah.
That there's a unique there's a unique stationary measure.
And there is certain form of unique ergodicity for the projective action.
But the measures are living on different fibers, so I'm not. I mean, there is some sort of unique object there, yeah. Okay. But I'm not sure the right way to say it. Just because everything's completely contracting. So this is our transversality. Transversality is this estimate here, that bad configurations happen exponentially unlikely. There will be some bad configurations, but they're exponentially rare. So I will say that we're following a big part of Tsuji's paper, where from the transversality, you're able to control some energy, and then you're able to get absolute continuity. Tsuji also works really hard to produce the transversality. We're kind of getting the transversality for free because of the linear data we're starting with, or from the uniform expansion in the past. But, well, I really enjoyed this project and learning this trick, or this argument. Yeah, this first Hilbert measure definitely lives on some Cantor set in the projective bundle. It probably is not absolutely continuous. You should definitely not expect that. But the base measure downstairs, that this is somehow parameterizing the directions of, somehow will be, like this is the dimension of all these lines that we're somehow convolving together. And there's one more question? Oh.
So you use that separation that you don't have lines in cone for the image?
We're definitely using that the two cones are disjoint, or they're eventually disjoint. Because if the cones were the same, then this would be a point mass, and then you wouldn't have decay. Yeah, exactly. We're definitely using, from the fact that they don't commute, the unstable eigenvalues point in different directions, so these cones eventually separate, and so then this measure really is not sitting on a point mass, it really is some sort of fractal measure. Yeah, thanks. Alpha is some sort of Frostman dimension, which might be a lot smaller than the Hausdorff dimension, and probably we can make this work with Hausdorff dimension, but we're happy with a Frostman dimension. Okay, now the one thing I'm going to be very vague about is what is a good measure. So I'm going to tell you what good curves are. So a C2 curve from 0, 1 to the torus is R good if, so what the key thing about being good is that the derivative is always inside of the unstable cone. So these curves, they're going to point inside of the unstable cone. The rest is mostly technicalities. I want the length to be at least R. So I didn't say it was a unit speed parameterization, so I want the length at least R. I want the curvature to stay bounded, and curvature is less than some K naught, which is something universal for the whole system. And then what I want to do is I really don't want to study curves. I really want to study densities on the curves. So a density, nu gamma on gamma, and I'll try to be careful to make my nus and gammas distinguishable. I should have chosen different letters. Is R good if the curve is R good. And here's where I'm going to be very imprecise. And the density, so this is some sort of smooth measure. The density d nu, oh, I need one more thing. So I'm going to say m gamma, this is the arc length measure on this curve. So I want to compare my mystery density. Oh, these look exactly the same now. D nu sub gamma, d m sub gamma. I want this density to be well controlled, and what you need is L log Lipschitz. If you've ever done an estimate like this, you sort of know that log bounded variation is sort of a good thing to work with. And I'm going to assume that nu gamma is always a probability measure. So you start with some good curves that are always tangent to the unstables. You put some density function on there, a reasonable density function that's not too spiky. And then finally, a measure nu on T2 of the form nu is going to be an integral of nu, all right, I definitely should have chosen better Greek letters, nu gamma, with respect to some distribution on the space of gammas, where nu gamma is R good, where every our nu gamma is R good is called R good. Okay, so what kind of measures are we looking at? We're looking at measures that are convex combinations, maybe they're discrete or maybe they're integrals of nice densities along nice curves. These curves are sufficiently long, they're not too crinkly, they have bounded curvature, they have nice length, they always point to the unstable cone, and we put a nice density on them. And then maybe we average a bunch of them together. And these are the kinds of measures that we want to study. And some facts about these is that if omega is in sigma n and nu is R good, then f omega star of nu is R good. So pushing it forward, because it's always tangent to the unstables, it's going to stay tangent to the unstables, its length is going to increase. The curvature isn't going to get too distorted. The density isn't going to get too distorted. And so this is a dynamically invariant object. And if nu has whatever the SRB property is, then nu is also R good for all R below some threshold. Okay, so bullet point D is, I'm going to be intentionally somewhat vague about this, but these are kind of the nice family of measures to work with. E is our inner product. So given nu1 and nu2 probability measures on the torus, the inner product between nu1 and nu2 with respect to rho is 1 over rho squared. Sorry, I'm going to have to write it here. 1 over rho to the fourth, the integral nu1 of a ball of radius rho at x times nu2 ball rho at x, and I'm going to integrate with respect to the Lebesgue measure of x. So I take how much mass does nu1 give to a ball of radius rho, how much mass does nu2 give to a ball of radius rho, integrate with respect to centers. What is the 1 over rho to the fourth? This is the Lebesgue measure of a ball of radius rho centered at x, quantity squared, maybe without the pi's. And our norm squared is just the inner product with itself. And we'll use that this is an inner product in a minute. And now I have mu, which is going to be 1/2 delta F1 plus delta F2. And my goal is to show some sort of La Sota-York inequality of the form that there exists some additive correction, there exists some multiplicative contraction, there exists some waiting time, there exists some thresholds for all, I'll write it this way, for all rho 1, there exists a rho 2, such that for all rho less than rho 2, I don't know why I'm being so technical here, for all rho 1 good measures nu, and for all, let's say all rho less than rho 2. if I take the norm squared with respect to rho, I have to push it forward by the dynamics, mu to the n of this thing. We see some contraction in the rho norm, in the strong norm, plus some additive thing. And the additive thing is supposed to come with a weak norm. And what is the weak norm? It's just the total variation. So this is just nu of the space. But this is just 1 anyway. So we'll just ignore the weak norm, because this is always 1. So this is what we want to show. And if we can show this, then we know that as we iterate this nu, its energy is going to stay bounded uniformly in all rows. This norm is going to stay bounded uniformly in all rows. And this will show that in the limit, this thing is actually an absolutely continuous measure. And then we can get absolute continuity of our stationary measure or any sort of limiting object of this process. So how do we use all the machinery so far on the board to get something that looks like this? But I'm happy to answer questions before I try to do functional analysis and inner products.
Can you explain why you have two O1 and O2?
Don't worry about it. Just because if you take a curve and you iterate it for a long time, it might grind around a bunch, and so then you want to chop it. And it's just silly things like this. So F, I'm not going to explain this one. This is the naive bound. So this is, I think I'm up to lemma 2. Did I have a lemma 1 somewhere? I don't know where lemma 1, oh, I know what lemma 1 is. I don't need lemma 1. So there's lemma 0 and there's lemma 2. Okay. If nu is rho 1 good, then for all n sufficiently large, for all omega words of length n, and for all scales smaller, and so we have to just, there's all these games of you have to go to some smaller scale depending on your n. Rho 1 over 2. I look at what my dynamics of an arbitrary word of length n does to my measure. I measure it in the rho norm, and this is less than some C1 j to the 7n nu in the rho 1 norm. Okay, what is the j? The j is sort of the maximum Jacobian of fi in ui. And so this is where dissipativeness is going to fight us. So dissipativeness is going to fight us because if we're too dissipative, this thing grows very large. But as fi go to ai in C1, j goes to 1. So j is at least 1 because you have some diffeomorphism. The Jacobian can't be can't be less than 1 everywhere. So there's just the determinant of the derivative. Uniform, the biggest overall points. This is somehow measuring the dissipativeness. And notice that there are two changes of norms here. I started with the small norm, and then I went to the big norm. And there's some monotonicity of the norms. That was lemma 1, but I won't write it. So this is less than C2. If I go from a bigger norm to a smaller norm, I expect things to increase. I expect the energy to increase. So this is 7n nu rho squared. So this is the naive estimate. If you do the dynamics on these things, you grow slow exponentially like the distortion, like the dissipativeness, the worst that the Jacobian can ever be. The weak norm is just total variation. It's just the mass of the space. It's very weak. It's almost silly I shouldn't have written it down. Here, if I have any rho 1, if the measure is rho good, if the rho is sufficiently small, then I have this kind of estimate. And there's a trick that you can always, up to a constant, you can always there's a monotonicity up to some universal constant. So the middle thing will disappear. Yes?
Here in this statement, you have to show at some point that the convolution of the initial good measure will converge to some good measure.
Yeah, but it'll converge in the end. Right now I'm trying to show that the finite time things have some sort of non-contraction.
But is it hard to show this part?
No. Okay, so now I want to split into two regimes. So take the norm, mu n convolved with nu, rho squared. Well, what is this? This is mu n convolved with nu, interproducted with itself. What is nu n convolved with nu? It is you push it forward under every word of length n and you average. We're interproducting with ourselves, so this is the sum over omega 1, sum over omega 2. These are words of length n, 1 over 4 to the n, interproduct, and this is the rho interproduct of f omega 1 star of nu, comma, f omega 2 star of nu in the rho size. And now there are two, I'm summing over all possible words of length n. Really over all possible pairs of words of length n. I can split the pairs into two pieces. I can first do, which one do I want to do first? I want to do bad ones first. I can split it over the pairs that are primarily pointing in the same direction of the same thing, plus the pairs that are pointing in opposite or transverse directions of the same expression. Punchline, this is going to give us our contraction in the strong norm. This is the bad regime. This is the bad configurations. But this is going to give us our contraction in the strong norm. These are somehow the good configurations. And this is going to give us just our C times the weak norm. So let me try to just really wave my hands, but try to convince you of these two things. But we're just taking a sum of a bunch of things and splitting it into the two cases. So after G comes F, I think. After G comes E, F, G, H. What?
The bad ones are the other.
Okay, somehow these are the bad because they have I can't control them. But it's going to give me the contraction because they're exponentially unlikely. These ones I can control. I can control the geometry of these things, and it's just going to give me something additive. Okay, so maybe what you consider good and bad is different from what I consider good and bad. But maybe I'll call it case 1 instead of good or bad. Case 1 is when omega 1 is pointing primarily in the same direction as omega 2. And here we just do the silliest thing. F omega 1 of nu paired with f omega 2 of nu in an inner product. How would you bound an inner product? Is you would use Cauchy-Schwarz. 1/2 the norm of f omega 1 nu rho squared plus f omega nu 2 rho squared. Right? I think that's called Cauchy-Schwarz from last time I taught real analysis. And then we have a really naive estimate on how this thing grows. This thing grows by a lemma from over there. So this is by, I think it was called lemma 2. This is less than some C2, something exponentially growing in the distortion, but then times the original thing that we had, the original norm. But this is just for a single pair. And how many pairs are there? There's exponentially few pairs. So the number of such pairs is small. So if we sum over all omega 1 parallel to omega 2 of this thing, and now I'm going to be a little bit sloppy and just start the thing from above. This is equal to, maybe it's even bounded, I think it's equal to, first summing over omega 2, all omega 2s, and then summing over this. I don't know, is this thing symmetric or not? But this is all omega 1s that are parallel to this particular omega 2. So this is probably bad notation, whether it's symmetric or not. Here I do mean all pairs that are pointing in the same direction. Here I just mean all the omega 1s that are, here I'll write like this. Omega 1 such that omega 1 is parallel to omega 2 of the same thing. But now we have a bound on this. There's at most, and what have I left off? I've left off a 1 over 4 to the n, a 1 over 4 to the n. There's at most 2 to the n of these things. And then there's something that's exponentially small in 2 to the n. This is like 2 to the n, 2 to the n, theta to the n alpha. Just because there's not very many things pointing in the same direction. And so this is less than or equal to, I'm just going to copy things now. The 2 to the n's, they cancel with the 4 to the n's. Theta and alpha, some nonsense constants, some Jacobian, and then the thing I started with. And now this theta somehow is uniform under my perturbations, because this regularity is a really strong property. But my distortion, I get to control. My distortion, I can send as close to 1 as I want by making my perturbations small in the C1 topology. Theta was less than 1. The Jacobian was bigger than 1. But now I can grab all of this stuff together. If I make J sufficiently close to 1, then I can call this thing and take n large. Then if I call this thing kappa, it's less than 1. So somehow pointing in the same direction is bad geometrically, but it's giving us our contraction in the strong norm just because we have some naive growth of this thing, but it's an exponentially unlikely event to occur. And that's just where we're getting the contraction from. And again, this is, this we adapted from Suji's paper, and I think it's a really beautiful argument. So, okay, after H comes I, but I was using Roman numerals, so maybe I'll call it J. So, case 2, which is omega 1 transverse to omega 2. And now, notice I'm studying over here, like pushed forward measures. Yeah. What do I want to say here? This expression here this is bilinear when I expand nu as an integral of nu gammas. So the nu is some average of nice densities on curves. I can take this thing and I can split it in both terms by the densities on those curves. So it's enough to replace this with a curve and this with a curve, and they can be different curves. So I can just take gamma 1, gamma 2, which are, they're going to be row 1 good curves, but because I want to iterate them, I want them to be not too long, so maybe the length is less than rho naught. And then, of course, you have to engineer these things. But I can just take these things and I can study this expression, f omega 1 star of some density on nu 1 and f omega 2 star of some density on nu 2. And if I get good control on this, then I just average over all the curves, nu 1 and nu 2. Maybe nu 1 and nu 2 are the same, I don't know, but they could be different. And what do I know? So somewhere over here is gamma 1, somewhere over here is gamma 2, and I apply the dynamics to them. I'm applying different dynamics to them. And I know that they, okay, if they don't intersect, then there's no contribution to the integral, so I'll draw the intersecting picture. And I know that if they intersect, the image curves, they intersect and make a big angle. So this is at least theta to the n. And now this says measure balls with respect to these curves. So if the center of my ball is here, then the red curve gives it no weight, and the blue curve gives it no weight, so I get 0 contribution to the integral. If I'm way over here, the blue curve gives it weight, but the red curve gives it 0 weight, so I still have 0 contribution to the integral. So what center points do I care about are just inside of some parallelogram. So here's a P, and only x in P are going to contribute to this norm. Because if I have the center outside of here, then one of these terms is going to be 0. So you take an x in here, and you take some rho ball. And now you ask how much charge does the pushed forward gamma 1 give to this thing? And maybe I'll come over here. So I already have gamma 1 over there, but I'm going to redraw it. So here's my original gamma 1. I'm going to pull back this rho ball, and how it looks something like this. So this is the pre-image under omega 1 of the ball of size rho at x, pre-image. And now somehow I want to know how much weight. There's a probability measure here, so how much weight is on here is just the proportion in there. I could also look at the proportion over here, and somehow I'm assuming that the densities are basically the identity. These are all technicalities you can work out. So nu 1 of this interval here, which is basically, okay, I don't know why I put it in color, but this is the same thing as f omega 1 star of nu omega 1 of the ball of size rho at x. This thing is like the length of rho 1. Well, it's like the length of I divided by the length of rho 1. And so it's bounded above by lambda u minus n rho. That's the length of this thing. And I assume that this thing had length at least rho 1. And so I can really bound how much weight is on here by just pulling it back. Oh, and one other thing before I go to the other board. What's the area of this parallelogram? It's something like rho squared theta to the minus n, I think, is there a good estimate on the area of that parallelogram. I'll take my notes with me. And so to finish the second bound, the good configurations is f omega 1 of the density on curve 1, f omega 2 of the density on curve 2 at scale rho. It's 1 over rho to the 4th. And I'll write it all out. So f omega 1, density of omega 1 of a ball at x of size rho, I think I'm putting the rho there, times f omega 2, density of omega 2 of the same ball of size rho at x. And now we integrate Lebesgue against x. This thing, each of these things is bounded above by lambda unstable to the minus n, theta to the minus n rho. Is there a theta to the minus n? Sorry, where's the theta to the minus n? Sorry, this is rho over rho naught. Yeah, there's no theta n here. This is over rho 1. And I have another one here. And so that cancels 2 of my rows here. And then I'm integrating over p. And so this is something like 1 over rho to the 4th. The area of the parallelogram is like rho squared, theta to the minus n. And then each of these terms is bounded by lambda u minus 2n rho squared over rho 1 squared. That's just multiplying bounds on these terms. And what's the important thing is that all the rows cancel. So this is less than some C naught, which is independent of rho. It depends on the n, it depends on the theta, but it's a fixed object that's independent of the rho. It is just a constant. And so now you can assemble. And in the rho norm, for some n, which we picked to get the contraction, we picked the n in case 1, convolved with a good but arbitrary measure that is good in some sense, for rho sufficiently small, we see contraction in the rho norm plus some additive constant, which came from the transverse case. This comes from the tangential case. And we have this thing. And I think Bruno asked a question. So this doesn't say that note that mu to the n star nu is not necessarily absolutely continuous. It just says that at scale rho, its norm is bounded. But as you get a smaller and smaller rho, maybe the norm explodes for a fixed n. But what you can say is that so any limit point of mu to the kn star nu, this is absolutely continuous. So we can build an absolutely continuous measure from this thing, but this still isn't dynamically invariant. Okay, so then to make at least Bruno happy, and any limit point of, let's take Cesaro averages, and I'll just take mu to the k convolved with nu, k from 0 to n minus 1. And here I took nth powers, but you can just smear those out, 1 over n. This is absolutely continuous and mu stationary. This is how you prove that mu stationary measures exist, is you do the Krylov-Bogubliubov. And so so what we've done is we've produced an absolutely continuous invariant measure, and we know that the SRB measures exist, and so those have to be in this class as well. And so this is how we show absolute continuity of these stationary measures in our paper, just following what Suji told us to do. Okay, thanks.